See, we are in theorem 1 now. We need to prove that every convergent sequence has unique limit, or else prove that a limit of a sequence is unique. See, to understand this one, you should know the definition of convergent first of all. So every convergent sequence, already what is given to us, that we'll write first. Given sequences, this sequence is convergent. It is given to us. So what we have to consider, let this convergent has, this sequence has, we need to prove that it has unique limit, single limit. So we have to consider, we can write, let us suppose that this sequence has two limits, say ln l dash. It has two limits, ln l dash, and you have to be clear that they are not equal. L is not equal to L dash. So we know that L is not equal to L dash. So we can consider this one as L minus L dash is not equal to 0. If I'll apply modulus to this value, modulus means positive, then this inequality will change. This not equal to will change to inequality, it is greater than 0. If L is 2 and L dash is 3, 2 minus 3 minus 1, again modulus will give you plus 1, which is greater than 0. So how to start this question? See, whenever you are learning any question, any theorem you need to write, what you have to keep in mind is which approach we are using. I am using this approach, contradiction approach. At the end, you will get to know what is that contradiction approach. Then to prove that sequence is unique, we have to start that unique means single, it has a single limit. But because we are doing by using contradiction method, what we are supposing that it has two limits. We need to prove that it has a single limit, but we are proving what? We have to consider what? We have, it has two limits, L and L dash. So this L and L dash is, L is not equal to L dash. So what we can write? L is not equal to L dash taken to left side, L minus L dash is not equal to 0. If I'll apply modulus to this one, this is greater than 0. Why we have taken modulus, you will get to know at the end. At the end of the theorem, you will get to know this. Now what is given starting given condition is Sn is convergent. Now we have to use by the definition, for each, what is the definition of convergent? You need to remember that epsilon greater than 0, there exists m belongs to n such that Sn minus L is less than epsilon. For, because we have two limits, we will take this one as by 2. For all n is greater than equal to m, but we will take m1 here because L and L dash both limits we have considered. So by definition, slightly definition will change. L is there and epsilon is epsilon by 2 because of the two limits we have considered. Epsilon by 2 you can consider. N is greater than equal to m means it is m1 now. Now for the second limit, by definition for each epsilon such that for the limit L we have taken this one also. By definition, first we will write Sn is convergent to L in first case. Also Sn is convergent to L dash. So we have for each epsilon is greater than 0, there exists m belongs to natural numbers such that Sn minus L dash is less than epsilon, because L dash and L both are limits, epsilon by 2 or epsilon by 3, any number you can consider, for all n is greater than equal to m2. So we have two cases here. Sn minus L is less than epsilon by 2 in first case, and Sn minus L dash is less than epsilon by 2 in second case. Once again check it out what we have done till here. See, in theorem 1, we need to prove that a limit of a sequence is unique, means one sequence Sn has one single unique limit, means one limit value. What is that one limit value? To prove that one, we are using this contradiction approach. So what we are considering, Sn is anyhow given whatever you can write. We are supposing that contradiction means we will suppose, if single limit we are proving, we will suppose that it has two limits L and L dash which are not equal. We will take to left side, we will have that one. So L minus L dash is greater than 0. Now in this case, we can also write, we know that if L minus L dash is greater than 0, since epsilon is also a positive real number greater than 0, therefore we can consider that L minus L dash is nothing but epsilon value. This also you can remember. Beside this you can write this. Now I'll write this first and second condition here. Now we have to consider m, anyhow we have taken m1 and m2 as natural numbers for two series, so you can write this statement once. Now we'll write, we'll take L minus L dash, we'll take from this one, L minus L dash equals to, now add and subtract Sn here, subtracting Sn, adding Sn, so minus L dash. Now you have to consider this modulus x plus y is less than equals to mod x plus mod y. So less than equal to, now this equal to changes to less than equal to modulus x plus modulus y. One more property of modulus is, if modulus x is given to you, x minus y is there, which is always equal to y minus x. We can reverse this one, because 2 minus 3 is minus 1, modulus value is 1, and 3 minus 2 is 1, modulus value, absolute value, positive value is 1. So we can write this one as Sn minus L plus Sn minus L dash. In equation 1, what we got, Sn minus L modulus is less than epsilon by 2. Clearly this one inequality, this equality will change to this inequality, less than, this equality will go less than epsilon by 2, plus this is also less than epsilon by 2. So what we'll get, modulus of L minus L dash is less than 2 epsilon by 2. Now L minus L dash is what value we have, I told you earlier, this is epsilon itself. Epsilon is less than epsilon. This is a, epsilon can't be less than epsilon, so it is a contradiction. They are equal actually. If this is a contradiction, we come to the conclusion that it has unique limit. See, if we have considered that it has two limits and we did some calculation, it is not acceptable. So we are getting that contradiction at the end. So we can come to the conclusion that it has unique limit. This is the proof for contradiction. So first thing you have to write, given Sn is a convergent, whatever given to you. Now you have to suppose, because we have to prove for single limit, because the unit limit is unique, we have to suppose that it has two limits, L and L dash. So L is not equal to L dash. This is the case which you have to remember. Then a minus L dash is not equal to 0. Then this is, if you apply modulus, it is greater than 0. The same thing, if it is greater than 0 means epsilon is also greater than 0. That's why we will equate these two values. L minus L dash is the value which is equal to epsilon. Now this is our equation 1. Then consider m, because we have taken m1 and m2 in definition. So m will be maximum of m1 and m2. Then modulus of L minus L dash we have to start. We have to take this value, add and subtract Sn in between. Then this equal to will change to less than equal to, because of modulus of, we are considering these first two terms as A, this as B. So we have modulus of A plus B or X plus Y equals is less than equals to modulus A plus modulus B. That's why this equal to will change to less than equal to. Then this less than equal to will change to less than. This is the main thing, inequalities. Sn minus L is epsilon by 2 from the definition. So you can remember in this way. To prove that every convergent sequence is bounded, first thing we'll consider proof. What is given in the proof? Convergent sequence. Given, what is given to us? Sn is convergent to L we will consider. So every convergent sequence is bounded, we need to prove, required to prove, I am not writing. Given that Sn is convergent to L, by definition we have to start now. By definition of convergence, for each epsilon is greater than 0, there exist m belongs to z plus such that Sn minus L is less than epsilon for all n is greater than equal to m. This is by definition we know. Now what you can do, we will consider one epsilon here, because to prove that it is bounded, we can consider any number for this. So you have to remember this, epsilon equals to 1, because any greater than 0 we have to consider. Now we can write this definition in this form, Sn minus L is less than 1. So to remove this inequality, what I told you earlier, if x is less than a, so minus a is less than x less than a. So less than 1 greater than is minus a. So to remove this modulus, we will take less than 1 and here greater than minus 1. What I told you earlier at the time of doing definitions problem, all definitions and problems are used in this one. To remove this minus L, we'll add L to this equation. This one plus L plus Sn minus L plus L plus 1. So that we can get this one, L minus 1 less than Sn less than L plus 1. So every convergent sequence is bounded, we are getting that these two are, the Sn is in between these 2 points, these 2 neighbors. So what we can consider, this one is for all n is greater than equal to m. For all n is greater than equal to m, for all values you can write this one, for all n is greater than equal to m. This one you need to write for every single equal to. Then put, I am taking L minus 1 is equals to k and L plus 1 is equals to another k. and K1 is equals to, because it is on left side, minimum of all the values, all values of sequence 1, 6, term 2, term 3 till n minus 1 term. K2 equals to maximum of, because it of right side, all values S1, S2, it is up to L plus 1. So we can say that if it is least value, minimum value, and this is maximum value, so Sn lies between K1 and K2. Therefore, Sn is bounded. So whenever you are learning theorem, first you have to check what we are using. Here epsilon equals to 1 we have taken. In previous one, what we have taken, previous theorem, for proving that it has unique limit, that time we have considered two limits. That form you have to remember. In this one, by definition, what we are writing, and to start the theorem, what we are considering here, epsilon equals to 1. That means for bounded, we can consider 1. We have other method also to solve this one, but this is the best method. You can remember easily. Simple theorems are there, short theorems, but anyhow it is there in your syllabus. If limit n tends to infinity, Sn equals to L, prove that limit n tends to infinity, modulus Sn is equals to modulus L. What does this means? Limit n tends to infinity, Sn is equals to L. This is used for convergence. If Sn is convergent, that time they will use this also, this notation also for convergence. So you remember, whenever we are using, given that Sn is convergence or convergent, this implies limit n tends to infinity, Sn is equals to L. So this is given to us. So what we'll write? First we'll write proof. In proof we'll write given. What is given to us? Limit n tends to infinity, Sn is equals to L. So this implies Sn is convergent to L. It converges to L. If it converges to L, by definition, we have for each epsilon, what I told you many times, you are going to use this definition. Epsilon is greater than 0. There exists n is greater than equal. There exists m belongs to positive integers. That means m belongs to n, such that Sn minus L is less than epsilon you will get for all values of n is greater than equal to m. So by definition we know that for each epsilon is greater than 0, there exists m belongs to z plus, and Sn minus L is less than epsilon for all values of n is greater than equals to m. After writing this definition, what you have to do is, we have to consider, we know that modulus A minus modulus B is always less than equals to modulus of A minus B. How do we know that? We have to consider that this one. To prove modulus on both sides, we have to consider any modulus inequality. So we have taken modulus A minus modulus B is less than equals to A modulus A minus B. Now, first I will consider Sn here and L in place of this. So this is less than equals to Sn minus L. So both are positive, and if we'll subtract also L is smaller than this, so this will get anyhow one more modulus here, positive value. Here no need, already full modulus is given to us. Now this modulus Sn minus L is what? Sn minus L separate modulus is less than equals to this epsilon. But here it is less than epsilon, so this value is clearly less than epsilon, so this inequality will change to equality, will change to inequality, less than you will get. Now you can remember what I told you earlier. Suppose we will get Sn minus 5. If it is less than epsilon, we can write Sn converges to this 5. Less than any value we can say. So what we can write, this value is L always. So Sn converges to 5. If Sn minus 0 is there, if it is less than epsilon, Sn is converges to 0. Then for this one, if I want to write in this form, if I want, so I can write modulus Sn converges to modulus L. Any convergence in terms of limit, how we'll write? We'll write limit n tends to infinity, this value is equals to this value. If I am saying that Sn converges, so what is that meaning? Limit n tends to infinity, Sn is equals to L. If Sn converges to P, that time limit n tends to infinity, Sn is equals to P. In the same way, by definition, if we are writing, we'll write in this way. In limits, if we want to write this one, we'll write in this way. So once we get in by definition, what we get to know, if anything here minus this one, S is series is given, minus any number is given, means this series converges to this number. This one we'll write in terms of limit in this form. So this is also proved. Same whatever we have done just now, whatever done in the previous theorem, same thing we'll do. What we'll write here? Proof. Then in proof we'll write given limit n tends to infinity, Sn is equals to 0. This means what? This implies Sn converges to 0. By definition, what we'll get now? By definition, for each epsilon is greater than 0, there exists m belongs to z plus such that Sn minus L is less than epsilon for all values of n is greater than equal to m. Now what we will consider when modulus are given to you? We have to consider, or we know that modulus A minus modulus B is equals to modulus of A minus B. Then modulus of Sn minus modulus of 0 is equals to modulus of Sn minus 0. So if they are equal, less than equal, we get to know that this inequality will change to Sn minus 0 is epsilon. So we get to know Sn minus modulus 0 is less than epsilon. Therefore, in what way we can write this one? Sn converges to this. This implies if I want to write in limit n tends to infinity, this Sn is equals to this value. This also proved. So 5 theorems videos you'll get from now. When you find limit n tends to infinity Sn is equals to L and limit n tends to infinity any value equal to L dash means convergence. This converges to L. This Tn converges, this series Tn converges to L dash. Then we have to prove that sum of both the series converges to L plus L dash. So we need to prove that we have already. So in proof we'll write given limit n tends to infinity Sn is equals to L and limit n tends to infinity Tn is equals to L dash. This implies Sn converges to L by definition for each epsilon greater than 0 there exists m1 belongs to z plus. Already I told you earlier also we have used this m1 z plus such that modulus Sn minus L is less than epsilon, but here two limits we have taken, so epsilon by 2. Earlier also we did one problem. For all n is greater than equal to m1. Here also what we have, this implies Tn converges to L dash by definition for each epsilon is greater than 0 there exists m2 belongs to z plus such that Tn minus L dash is equals to is less than epsilon by 2 for all n is greater than equals to m2. So we have to, when m1 and m2 are introduced, always you can write m is equals to maximum of m1 and m2. This is the rule of writing this one. Once we have two values, now you can consider what we have to get the answer. We need to get this Sn plus Tn. So to get this one, we can write this value I will consider to left side. Sn plus Tn minus L plus L dash. This equals to Sn minus L plus Tn minus L dash. Purely you have to consider this. The left hand side is there, not take this right hand side to left hand side and consider this. Now this will be less than equals to modulus of a plus b is less than equals to modulus a plus modulus b property. Modulus Sn minus L plus modulus separated for this one. Then less than equal to will go now because this value is less than epsilon by 2. This is also less than epsilon by 2. this is less than 2 epsilon by 2 less than epsilon. So we got Sn, if I will simplify and write this one, without simplifying and writing, Sn plus Tn minus L plus L dash is less than epsilon, is less than epsilon. Suppose if I'll write any sequence minus any number is less than epsilon, means this value converges to 4. Similarly, if I'll write 5 here, Sn converges to 5. Same thing, if this is one series, suppose this combination of both series is one series minus this combination of both L is single L, that means what we'll write, therefore Sn plus Tn converges to L plus L dash. This implies, if I want to write in terms of limit n tends to infinity, Sn plus Tn is equals to L plus L dash.